Got it. We got it working.
Okay.
I had put, instead of I had put an N, and that goofed everything up. Okay. So we see initially our number 2 has the largest number. When I take total divisors divided by 2, it gives me 1.5, then 1.8, then 2. 6 is when the first number where you get above 2.
Or at 2.
60 gets to 2.8, but now I can go up to 1,000. Oops, now I can go up to 1,000. Oh, now I'm above 3. Now I can go to 10,000. See, do I find a number above 4 yet?
Not yet.
100,000. Oh, there's the
4
first one above 4.
2.
25,200. So maybe that was up in our chart, one of the numbers up there.
That could be like, maybe that one.
Yeah, it could be that one there. We saw a dot right there. Maybe that's the first one above 4. So that's interesting. So it says when I take the number 25,200 and I sum up all the divisors, I get about 4 times the number. Maybe I'll go to print out to 3 decimal places. Oh, it's actually 3.97. So actually 27,720 is the first one, where it's above 4. It's 4.05.
Then you get 4.19.
Yeah, then I get 55,000. Do you think it ever gets above 5?
Maybe for 1 million.
Should I go up to 1 million? Let's see.
It's still running. 4.29, 4.23, 26, 4, 4, 5, 1. Is that it? Yeah. Not yet. Gets up to around 4.5.
Yeah. So it turns out that this middle number, the number in the middle column, the ratio of the sum of the divisors to the number, that there are numbers that make this ratio as big as you want. But it takes longer and longer and longer for them to grow big. And the shape of that curve is very special. And these numbers themselves are also very special. They're called superabundant numbers.
Superabundant.
Superabundant numbers. And they were studied by Ramanujan. And they are one of the keys to something called the Riemann hypothesis. And if you can figure out how these numbers in this list grow big, then you would be able to solve one of the most important unsolved problems in math. If you figured out like exactly how these numbers formed in this list. So there will be a number that's bigger than 5.
Eventually.
But I don't know, maybe you have to go to 10 million.
It's going to take a long time.
Where the ratio is bigger than 5, but there'll be one that's bigger than 6. There'll be one that's bigger than 7.
Eventually.
Eventually.
I think like the bigger they get, the slower it takes to grow.
Yeah, in fact, this is also related to the harmonic series, the sum of the inverse integers. It has the same property. It grows. That sum grows as large as you want it to grow, but it just grows slower and slower and slower over time.
That sum's taking a while.
I don't know if the computer can handle it.
I can definitely handle it. It just goes very slow. And my way of doing this is also super duper slow because it's checking every single number. But look, 2,162,160, 4.62 is the ratio.
Interesting.
But these numbers seem pretty random, right?
Yeah.
Yeah, I mean, they don't look that special.
Let me just stop. But let me show you something really cool about these numbers. We'll just look at the last couple, all right?
Yeah. Okay.
21, 2162160. That's the number there?
Yep. 243357171.
So what does that mean?
2, 3, 5, 7, 11, 13. Those are some of the first primes.
Yeah. 1, 4, 4, 1, 4, 4, 0. 2 to the 5th, 3 squared, 5 to the 1, 7, 11, 13.
Wow.
Cool. We're using the first 5 primes.
Yeah, so something is special about these numbers. They're not complicated numbers. They don't have really crazy. Like a number in the 2 millions might have a prime factor that's really large.
Yeah.
Yeah.
Like, certainly you would expect maybe in the hundreds. But these numbers don't.
They're pretty simple, actually.
Pretty simple numbers. So it seems like this should be a simple problem because you're looking at very simple numbers.
But I guess they're complicated.
But it turns out to be slightly complicated. And in fact, I might still have it up on the screen. This is the 2000th number in the list. Oops, what is this? This is the 2000th number in the list. You ready to see this number? Ah, shoot.
Okay. You're copying the link.
Actually, you know what? I'm going to put it into factor integer.
Whoa.
That's a large number.
That's a large number, but let's see how it factors. 2 to the 12th, 3 to the 7th, 5 to the 5th, 7 cubed, 11 cubed, 13 squared, but it goes all the way out to
691.
691 to the first power. But it still factors in a pretty simple way.
Yeah.
Right, this is I think this is 300 digits long. Take the logarithm of it in base 10 to get the number of digits. $310 digits long. But the highest prime that went into it was 610.
Wow.
Like it seemed like there were a bunch of primes. Just a bunch of primes, like no prime squared. There were a few, but not much.
There were a few. So these are called the superabundant numbers. And studying sums of factors leads you very quickly to an unsolved problem in math. It's pretty cool.
Cool.
Alright, good work this morning, guys.